Hello everyone again. Thank you for joining. Uh, this is the third meeting of our journal club. The first two were in Bangla, but this one we are doing in English because as I've already told you that there will be two types of things in these journal club meetings. During some weeks we'll present a paper ourselves, so one of our members might present a paper, and those meetings are usually in Bangla. But this one is in English because during some of the meetings we will invite someone to present her or his recent work or any work actually. And in usually those meetings will be in English because there are not many. Well, probably there are almost no professional astronomers in Bangladesh, so we have to invite someone from outside. Well, there are Bangladeshi students who are studying abroad, so probably they can speak in English. But in other cases, this will be in English. So this is the first in that author series where we are inviting someone. In this series, we have invited Payaswini Saikia. Hi, Payaswini.
Hi.
So she's working as a postdoctoral associate at New York University, Abu Dhabi, since 2018, right?
Yes, 2018.
Yes. So before that, she did her PhD from Radboud University in Nijmegen, Netherlands. Actually, we did our masters together. There was a Erasmus Mundus master's program called Astromundus. So it's a scholarship given by the European Union for people, especially for people outside Europe who want to study astronomy or astrophysics. And I think we're the first batch in that Astromundus program. So we finished masters together, and actually we also both of us did PhD in the Netherlands, but in different universities. After that, well, I went to South Africa. She's now in Abu Dhabi. So her work is, well, I think it will be better if she introduces her work. Today we will hear from her what she has done during her PhD mainly. Of course, I hope that Payaswini will be willing to even come back in a future meeting. So in that case, in a future meeting, she can even present more recent work that she has done. But today we are starting with something simple. Not simple, something that can be explained in a better way to especially undergraduate students, because most of the participants here are undergraduate students. So she will try to present her PhD work and also the work that she has done related to that. And it will be introductory, so nothing very complicated. But of course, when you try to present your own work, you have to mention some specific and complicated things. But I think if you understand the basic, you will be able to at least grasp the actual work. So before beginning, maybe I'll ask Payaswini how everything is going in Abu Dhabi.
Okay. So in Abu Dhabi, well, hello everyone. It's nice to be with you all. So in Abu Dhabi right now, the numbers of COVID-19 are going, like it's better now, but our university is still closed. It's open only for the people who are doing lab work or experimental work. So I still can't go to office. I'm working from home, and it's difficult to, I don't know, concentrate in work when we are at home. How is it there in Bangladesh right now?
Well, almost the same, but I think it has the number of new cases has decreased a little bit. But yeah, I think many places are opening, but universities are still closed. So we are doing it.
Same.
And one good thing of COVID-19 was that we were able to begin this online thing. So it had one advantage actually, that people are opening up online more.
Yeah.
Probably I wouldn't have this idea if there was no COVID-19.
Yeah. Well, the sad part is that you already said that you're not going to invite me to Bangladesh now because I can be available online. That is the sad part, but yeah.
Well, I hope you will come physically sometime. But then the sad thing will be most people here will not be able to see your lecture because of course we can stream it online, so that's fine. But you are welcome to come anytime.
Perfect.
Great. At IUB as well. So I think, and well, maybe I should also say a few things about how many people there are. So there are around 40 participants until now, which is a good number. I think that this is the highest number that we have had so far. And as I have said already, most of the people who are attending are undergraduate students, first year, second year, but there are a few high school students, and also there are a few senior undergraduates from final year, and also maybe 2 or 3 master students as well. And
Okay.
most of them are from physics and engineering background. So,
okay.
you think
So
that
for the parts, so for the starting like introduction part, I will be speaking almost like a public talk kind of thing. So that would be understood hopefully by the high school students too. So sorry to the master student for that part. And there will be in the talk some parts in which we will be using some like, graphs and stuff, which might be difficult for high school students to understand. But do stay put, because in the conclusion part, we will go back to talking normal again.
yes, that sound, I think. So you can.
Okay, and also one more thing, when I'm giving kind of a talk or something, I get nervous quite easily, so I tend to speak quite fast. So stop me in between if you have any question. If I'm getting too fast or anything, just stop it. We are trying to make it informal as possible. So let's make it more of an interaction session than just a lecture, like one person speaking.
Yes, so that we can understand
Okay.
something, and then if we understand a bit of what we're doing, we'll be able to understand our future talks. With too much at the moment. Okay.
Sir, in light of keeping things informal, can I just say it's a pleasure to have you, Miss? And I don't think there's really any reason for you to be uncomfortable here, because we're all just pretty much students. It's absolutely
Great.
fine.
Thanks,
But it's nice to have you.
Thanks a lot for
Thank
saying
you.
that.
Okay.
Okay, so Khan, you want me to start with the presentation?
Yes,
Or?
yes, you can start now.
Okay. Oh, I think, wait. Let me know if you can see my screen.
Not yet. Yes, we can see now.
Is this fine, or should I make it bigger or something?
This is fine. This is fine.
Perfect.
This is fine, but
Okay.
maybe full screen would be even better. But up to you.
Yeah. Okay, I'll just make it full screen. Works?
Yes. Perfect.
Great. Okay, so welcome everyone to today's session. We are going to talk today about disk jet coupling and mass scaling of black holes. So we start with a general introduction to the black holes, which will be for both high school students and all of you present here. Then we move on to talk about the motivation for the paper. So basically the theory or the literature that we have for jet disk coupling and mass scaling. Then we move on to talk about the paper itself, about the optical fundamental plane of black hole activity. And finally, there will be a conclusion part talking about the summary of the work and having kind of a discussion with you all. Okay, starting with the general introduction part. So gravity is the force that keeps all of us intact to the earth, like it stops us from flying away. Now, the more massive or more dense an object is, the more gravitational force it has. So one of the object which we know has really high gravitational power is a black hole. So black holes are tiny spaces which have such enormous density or mass that it has tremendous gravitational power. And by tremendous, I mean that it does not let even light escape its surface. And that is a problem, because I am being able to see you because light falls on you and gets reflected back to my eyes. Now, if there is no light that can escape the surface of a black hole, we can't really directly see it. That makes it a very interesting and a really challenging subject of astrophysics and science in general. So where these black holes are, like we knew that there are black holes theoretically from a long time, but now we are finding evidences that there are astrophysical black holes out there, and quite a lot of them actually. So, like our galaxy is the Milky Way, Similarly, there are thousands and thousands more galaxies like this in the universe. And we think that in all these galaxies, at the center of the galaxy, there is a supermassive black hole in it. By supermassive, I mean a mass which is like millions of times more than the mass of our sun. So these supermassive black holes kind of keep the whole galaxy intact. Just like, in the solar system, there is the sun, which has a gravitational power, and with its gravity, it keeps the whole solar system intact around it. Similarly, these supermassive black holes keep the whole galaxy intact. Along with these supermassive black holes, there are also many smaller black holes which are scattered around the galaxy. So these smaller black holes are formed when there is a star which is like 10 times the mass of the sun dies. So there are many of these black holes. Like every time a very massive, like a supermassive star dies, these black holes are formed, but we can't really see them because of the exact reason that we talked about, that it does not let light escape. But whenever there is some cloud of gas or some star or something comes to the vicinity of the gravity of that stellar mass black hole or the smaller black holes, it starts to eat up that star or that cloud of gas. And while doing that, it produces really, it like makes the gas super in temperature, and we start to see it in different telescopes with different wavelengths using, for example, radio telescope or infrared or optical that we will talk about later in the talk. So these are called as stellar mass black holes. So we have supermassive black holes, which are like millions of times massive, and we have stellar mass black holes, which are like 10 times more than the mass of the sun. Now, although there are a lot of differences between these two, like the temperature will be different, the size, the mass, the origin probably, the evolution of these black holes, a lot of things will be different. But just the simple fact that these are all black holes, which are accreting matter and which are like sometimes like producing some jets or some things like that. So we think that in the simplistic picture, there should be similarities between these two. But most of the times, there are people who study the supermassive black holes separately, and there are people who are studying the stellar mass black holes separately. The idea is that if we can find a proper similarity which can be shown using formulas, then it would be really interesting and informative because we know a lot of supermassive black holes. So we have a huge statistical sample to understand about black holes using these supermassive black holes. We don't know so many of stellar mass black holes, but whatever we know, it's really easy to follow because these are smaller black holes. So their evolution cycle is easy for us to see in our own lifetime. Like in few years, we can see how it is evolving. Supermassive black holes take like ages to evolve. So it's difficult for us to understand them or study them. So if we can have a proper empirical formula or a proper understanding of how we can use the knowledge base we have for stellar mass black holes and the supermassive black holes together, then we can actually know about these black holes much more. Okay, till now, is there anything that you want to ask or you have any question? If not, then I can move ahead. So when I say that we should have a simple understanding, like in the simplistic picture, it should be, the physics should be similar for both of these kind of black holes. In the simplistic picture, there are actually mainly three components in a black hole system. One is the black hole itself. One is an accretion disk, which is formed around the black hole when it starts to eat up a star or a cloud of gas or things like that. And the third is a relativistic jet that comes out sometimes from the black hole system, not from the black hole itself, but from the system during its evolution, during the evolution of the system. First, let's talk about the accretion disk. So when there is a black hole and it starts to eat up, for example, like some gas or surrounding matter, then you know about the angular momentum conservation. So basically, it can't just eat up the whole thing at one go, like whoosh and gone. That cannot be done because there is some angular momentum that needs to be, like that needs to be conserved in a way. So the accreting material, it kind of forms a disk before getting completely eaten up. It forms a disk of material which is surrounding the black hole, and it starts rotating before it gets eaten up. And so when these different gas layers or matter layers of the accretion disk, when there is friction caused by the turbulent velocity, then this angular momentum from the inner region of the disk can be transferred to the outer region. And that's why the black hole can finally eat up the matter. So basically, for you, just like for at least for the high school students, just know that the way we have angular momentum conservation or energy conservation, so just for that, there is an accretion disk that gets formed before the black hole eats up the matter. The second thing is a relativistic jet. And that is really interesting because so these jets are really very highly powerful. And we don't really completely understand how they are formulated, how they are originated and stuff. We have a basic idea. Of course, there are a lot of scientists who have been working since like 70s to understand these jets better. We know that maybe it's because of the spin of the black hole or because of the magnetic field of the black hole system of the accretion disk, that sometimes matter from this accretion disk or the corona that surrounds the black hole can get out, like the plasma, it can get ejected. And these jets, they are mostly seen in radio telescopes because they emit synchrotron radiation, which is easy to be observed with radio telescopes. And when they go far away from the black hole, these jets, which is a very like highly collimated jet of plasma, they start to interact with the environment. They can't expand freely anymore. It hits the interstellar medium and the jet gets decelerated, and we get like beautiful, large, prominent radio lobes. Can you see this? Can you see the marker in the?
Yes, yes, we can see the marker.
Okay, perfect. So these are basically the lobes of the jet that we can see. Here will be the galaxy or the black hole, and as you can see, at first the jet moves really collimated, and later it makes these kind of beautiful radio lobes. So these are the main two things. One is the accretion disk, and the second is the relativistic jet. Now, they emit in different wavelengths. For example, if you want to look at this accretion disk,
maybe it would be interesting to mention the scale of these things. So, for example, if you're talking about a supermassive black hole, an accretion does an accretion disk actually take up the whole galaxy, or what part of a galaxy?
Okay. So accretion disks are actually, compared to a galaxy, really small. So for example, when I showed this picture, I kind of exaggerated a lot, like a Bollywood movie. Sorry about that. So we have the black hole here. We have this complete galaxy here. And the accretion disk will be just a very small, tiny part of it. But the jets can go really high, like really far away from the, like I will show you the picture. So this whole thing is the galaxy. So the jets, especially for some types of black holes, like we say FR2 and stuff, or quasars, they can go really very, very far from the galaxy itself.
Yes.
Miss, so is this was that picture of to scale image, kind of?
So this one, no, this is just one picture actually. Maybe I don't know if they've made proper, like, you know, what is it called, the like
Scale.
different pixels to put everything together, but this is not a scale, like this is a proper real image.
Okay.
It's an actual observation.
Sorry, I could not hear.
No, I just added, so it's a real observation. So
Yeah. This is a real observation, yes. Okay, so moving ahead, if we want to look at, for example, the accretion disk, black hole we can't see, fine. But if we want to look at the accretion disk, we normally use either optical telescopes, which shows the outer part of the accretion disk, or X-ray telescope, which shows the innermost accretion disk, because, you know, like closer to the black hole, it's much more hotter, the material. So they start emitting not in optical, but in X-rays, like, you know, really highly energetic particles. So we have X-ray telescope to look at the inner accretion disk, optical telescope for the outer accretion disk. And if we want to look at these jets that I had showed, the best telescopes right now that we have are radio, sometimes infrared, but mostly radio telescopes. So just looking at optical, probably we can't see most of these jets so beautifully. Like this picture, for example, I love that observation. It looks so beautiful. For this, we need radio or infrared kind of telescopes to see these elements properly. Okay, so now we will move on, but is there anything you wanted to share or talk about either the disk or the jet or the black hole itself? Any one of you?
Sir, I just wanted to know why exactly is it that we can see these only in radio?
Okay, yeah, that's actually a nice question. So these jets, when they come out, they are, okay, wait. Yeah, so these jets, when they come out, they are, there are lots of shocks which happens to the electrons in that plasma. So they kind of emit a radiation known as synchrotron radiation. So for bachelor students, probably you have an idea of synchrotron radiation. So these synchrotron radiations are produced when these electrons move in a magnetic field. Like when we have an accretion disk, which is rotating, there is also magnetic field to the system, which also rotates. So we think that this magnetic field, the rotating magnetic field, kind of forms a cone like this, which helps these electrons escape. So they emit mostly in synchrotron radiation, which can be seen by radio telescopes or sometimes by infrared telescopes. That like the synchrotron radiation is difficult to observe with optical and X-rays.
All right, got it. Thank you, Miss.
Okay. Is there anything else?
Hi, ma'am. I am not from physics or astrophysics background. So my question is, how can a black hole really create a hole in a empty space? So I think you understood my question.
Yeah, yeah, I know. I don't know how to explain it easily, but because it's really a difficult question. So basically, for example, when a star dies, let's talk about just the stellar mass black hole. When a star dies, so what happens is that there is a star which is normally emitting radiation. So there is a gravitational force which keeps the stellar, like the star to which makes the star to want to die in itself, like because it has so much of high gravitational power. But there is also radiation coming out of the star, so it kind of balances and the star keeps intact like a normal sphere. But when there is no more fuel in the star, then the radiation dies off. So the whole mass of the star collapses into itself because it has so much of gravity in it. And when that happens, it kind of forms a supernova or something, which like basically emits all the outer, like the atmosphere or something of that star to the outside world. And the core of the star, depending on the mass, can either become a kind of a neutron star, which is also a very, very compact matter. Or if it is more massive, then it can form like a black hole. So black hole is not really a hole in itself, but yeah, I don't know how to say it. But it's so compact and we can't really see it at all. Like there is no material or no light coming out of it.
Maybe we shouldn't take that whole literally. It's more like it's something, maybe we can say it's something missing that we can directly see. So we are using hole as like a metaphor.
Yeah, we can't really see anything there. So it's like a hole and everything is being eaten up by it. So it's like a hole, like.
And of course, the black holes will be created by mainly merger of many different black holes like that, right?
So again, for supermassive black holes to form, it's not again exactly known how they're formed, but we think that there are mergers of different black holes, and probably that is how they're formed.
As we're speaking to supermassive black hole, I have a question. So why do we see supermassive black holes mostly in the center? I mean, if you think of it as a merger of black holes, so shouldn't it be popping up in random places across the galaxy? Why does the merger has to be in the center?
Yeah, that's a good question, but you need to understand the chronology. So basically, first we think, okay, again, this is completely thought experiment. We have some evidences, but it's not completely known. But it's normally it happens that first these black holes are formed, and because the black hole has such high gravitational field, so it eats up some of the matter and grows, and it, like, for the further part, it at least keeps those brings the matter nearby, and then like they at least rotate around that black hole because of the gravitational power of the black hole. So even if like something is formed, like it doesn't form out of nowhere, but if there is some merger or something happens, for example, there are right now 2 galaxies with 2 black holes in the center, which is already in the center because the black hole has such gravitational power that everything is attracted to it and everything is like, rotating around it. So now if these 2 black holes merge, then also the material of like, the galaxy, like the other galactic material, which is around these black holes, they will again be centered around that supermassive part, basically, again, the black hole. So it's not like why we have black holes only at the center. It's that all the other things are being rotated to the black hole, like, is being rotating around the black hole. I don't know if that made sense.
Okay, yeah, that made sense.
Okay.
That was a stupid question now that I think about it.
No. It's normal. Don't worry. Okay.
Hi, ma'am. I have a question.
Yeah, hi. Sure.
Where the accretion is created? Near the...
Sorry, we can't hear you. Are you speaking?
Hi, I missed your voice.
Okay, now?
Yeah,
Yes.
now it's better.
Where the disk created? Near the event horizon, inside or outside it?
Oh, so its event horizon is much smaller compared to the disk. So whenever a material from the like gas or anything from the disk enters the event horizon, then it is sucked up by the black hole. So there is the black hole. Outside is the like event horizon, like the boundary in a way we can say, and like it's outside of this event horizon that this disk is being formed. So anything inside the event horizon, it can't come out. So we can't really see it like a disk or something.
Basically,
Thank you.
basically, if you can see something, that's not inside the event horizon.
Yeah. Okay, I'll move ahead a bit. We will keep the discussion. We'll keep continuing the discussion though. So, okay, we talked about the black hole. We talked about the accretion disk. We talked about the jet. Now, when we look at the stellar mass black holes, which are also known as X-ray binaries, so when we look at these smaller black holes, we see that there is a tight coupling or pairing between the jet and the disk. So here we have the X-ray luminosity, and as I said, X-ray comes very close to the black hole in the accretion disk. So it kind of gives an estimate of the power, the accretion power of the disk. And we have the radioluminosity, which is the power of the jet. And we see that there is a correlation, quite a tight correlation actually, between these X-rays, which is y-axis, accretion power, and the jet, which is the radioluminosity. So here I'm just showing one of the best studied X-ray binaries called GX3394, but many other stellar mass black holes also follow this relation. So we see this in stellar mass black holes, this kind of jet and disk pairing. Do we see the similar thing also in supermassive black holes? Okay, so it was tried, and we see that, okay, these black ones are the X-ray binaries, and these colorful points are the supermassive black holes. And as you can see, they do follow the similar trend, but they're not exactly at the line that is shown by the X-ray binaries. So at a given accretion power, the jet power for supermassive black hole is much higher than what we would expect naively by just looking at the stellar mass black holes. But if we add another thing to this analysis, just another parameter to this analysis, everything lines up, and that is the mass of the black hole. So now here, in addition to the X-ray luminosity, radioluminosity, imagine this as a 3-dimensional plot, and we have the 3rd dimension as the mass of the black hole. If we do that, so basically we scale the X-ray luminosity with the mass of the black hole, then everything lines up perfectly. Well, perfectly is a very non-scientific word, but I mean statistically significant correlation is formed. So here now we have these X-ray binaries again, and we have the AGN, and it's the same as the previous plot where we have radioluminosity at x-axis, and in y we have accretion, that means X-ray luminosity. The only difference is the y-axis we have now scaled by mass. And all of these, both the supermassive and the stellar massive black holes, form a single plane or a single line. That is the basic of the fundamental plane of black hole activity. And at least for me, when I started working in astrophysics, this was really interesting to see, because everything, the whole sample that we have of supermassive black holes, shown here in colorful plots, and the black points here, which are stellar mass black holes, they are agreeing to a simple normal physics that, okay, the radioluminosity, which is the jet power, the X-ray luminosity, which is the accretion power, and the mass of the black hole, together, they are coupled for both stellar mass and the supermassive black holes. This was one of the studies which have shown kind of unification of these black holes or mass scaling of black holes. There are many other studies, actually. I will tell you about 4 of those now. I won't get into too much of details about these 4 different examples because these studies are not done by me. I'm just telling you from the literature survey that there have been other studies also which are trying to find if stellar mass and the supermassive black holes are actually doing the same things, like, you know, are governed by the same physics or not. So I will just mention very briefly.
Sorry to interrupt. I had a
Sure.
question in the previous plot.
Yes.
Is the luminosity in the y-axis is Eddington luminosity or general luminosity?
No, this is just the observed luminosity.
Okay.
For both radio and the X-ray luminosity, this is just what we're observing.
Because for black holes, we generally measure the accretion luminosity, which is the Eddington luminosity. So that's why
Yes.
I just.
Ah, okay, great. Yeah, but no, here we are just using like whatever we are observing, we are just putting it here.
Okay.
We have not converted it, but yeah. Okay. Okay, so I will now tell about 4 examples. Don't worry if you don't get to understand everything about that. Even I don't understand properly, but I'll just mention so that you know if you want to learn more, you can like read the papers. So the first one is that all these black holes, both stellar mass and the supermassive black holes, they're highly variable when we look at the X-rays. Like by variable, I mean sometimes they are very like high X-rays being emitted, sometimes very less X-rays emitted. But when we look at these X-ray light curves, how they are variable, we see that both AGN, that means supermassive black holes, and the stellar mass black holes, their power spectral density are very, very similar. So McHardy et al. 2006, which is a project done in the UK, they found that the variability plane, there is a very nice plane again by both AGN, that means supermassive black holes, and the stellar mass black holes when we look at black hole mass, accretion rate, and the time scale of this variability. So this is another addition to what we know about unification of black hole. Then there is another paper, again, not paper actually, there are many projects who are trying to work on this. This is a work led in the Netherlands by Elmar Keurding. So normally, we know that stellar mass black holes, they kind of, when they evolve, they follow a very simple pattern. All these stellar mass black holes. They are first, you don't have to understand too much into this, but just to give you an idea, they are first very quiet. Then the X-ray luminosity starts to increase. And at one point of time, the jet comes up. And then X-ray luminosity starts to decrease, and it comes back, and it follows the same loop again and again and again. Now the question was, do we see same kind of evolutionary behavior also in the AGN? Now that is a difficult question to answer because stellar mass black holes, we can see the evolution. It happens in few years, like, you know, sometimes just 2 years, we can see the whole black hole moving, this whole evolutionary track, coming back, going again. But supermassive black hole, they take like millions of years to do that. But there was a paper by Elmar Kjørding, led by Elmar Kjørding in 2008, and he used some Monte Carlo simulation and used some generalization of these different measures of hardness. And by using some almost 100 of active galactic nuclei, they found that there is a similar kind of trend also in AGN. But this is a completely statistical study. We are not able to follow one AGN properly to see if you can see this kind of evolutionary behavior or not. But this also is another example on how unification also in evolutionary trend is possible. Okay. There are another example, for example, in which a team of scientists, they looked at black hole X-ray binaries or stellar mass black holes, and they saw that the X-ray flux, which is how much of X-ray it is emitting, is highly correlated to the RMS or the noise in the amplitude. And similarly, this is also seen in different black holes now. So this is another work which shows that yes, unification is possible, probably another evidence for unification. And another work, this was actually led by my current professor here in Abu Dhabi. They looked at the different spectra of jet. They looked at where the spectra is breaking, at what frequency, and they saw a similar correlation, like a same correlation followed by both these AGN or the supermassive black holes and the stellar mass black holes. So there are a lot of things, a lot of different evidences who are trying to look at mass scaling. But because of time, I won't get too much into them, and we will move on to what we did. So
maybe I can
you remember this? Yeah.
Here for the students. Sure. So because this unification would be very interesting, of course, because probably Payaswini remember that we used to think that like while doing masters, this AGN is a very messy thing. It compared to stars, for example. We understand the structure and evolution of a star very nicely, but we did not understand the same thing for AGNs, for galaxies that have black holes inside. But it seemed that is seeing those diagrams that AGN community, of course, probably is moving in the same direction, that there would be not as rigorous as stars, but at least there would be a unifying description in terms of physics of everything related to black holes and there. So the unification is very important, I think.
Yeah, that's a nice addition, actually. Also, not just very important, but also beautiful in a way, you know, like, because we have black holes, we think that, oh my God, okay, there are jets, there are disk, wind, and so many things, and it's so messy. But the whole idea that there is a very simple physics, which is governing both of these huge things that we don't understand about. So that whole idea is like, you know, really pretty or beautiful, whatever you say. Okay, I should be more scientific while speaking about these things. Okay, moving on. Now, you remember this fundamental plane of black hole activity that I talked about? So in that, we were using, for looking at the disk as a proxy of the disk or the accretion power, we were using the X-ray emission. That is awesome. That's a direct way of finding out how powerful or how fast the accretion rate of this accretion disk is. But to get these X-ray observations, we need to go to space. We can't observe X-rays from the ground-based telescope. So it's a really expensive affair. So we thought that we would be using, instead of X-ray, another parameter to indirectly get an estimation of how powerful the accretion disk is. So, you know, like we talked about the jet, the black hole, and the disk. That is the simplest kind of the most, how's it called? The simplest description of the system. But there are also many other clouds and stuff which stay near to this system, especially in the supermassive black holes. And when, for example, light comes through these clouds, and you know the idea of a spectra. So when we see the light coming from these clouds, some of the elements in the cloud, for example, the O3 line specifically here, the oxygen content in the cloud can be seen in the spectra as either some emission line or as some absorption line. So the power of this accretion disk, basically, or the ionizing radiation that is produced in this flow, they can excite these O3 lines here in the gas, in the clouds, and we can measure this O3 line. So we thought that, okay, if it is not X-ray, but the physics behind the X-ray is the reason why we have this fundamental plane, then let's use that and try to see if we can get the same kind of plane also by using O3 line and not using X-ray at all. Because if we can do that, it would be really nice. Like O3 line, we can see from ground-based telescopes. It's not as expensive, and plus it would be great to see if the physics behind the fundamental plane is same as we have been thinking. So we took a sample of some local galaxies which are not high luminosity, but normal low luminosity, for which we have radio observation for O3 observation and the mass of the black hole. And just by looking at the supermassive black hole, we see that they do follow a trend. So normally in this fundamental plane, we are fitting both X-ray binaries, the stellar mass black holes in black, and the supermassive black hole. Now, we are just looking at the supermassive black hole in the 3D plot. Here is just a snapshot. And we see that they do follow a kind of a trend. Okay, that's good. So we fit just the supermassive black hole, and then we extrapolate it to the lower mass region. And we think that, okay, we pray that, okay, please, stellar mass black holes be in the same plane as this one, as the supermassive one. And voila, it actually did. And this was my first project as a PhD student. And you can't imagine how excited I was when we saw this, because previously, all the fundamental plane equations or studies that we have been doing, we used to fit both these stellar mass and the supermassive black holes. So it was like for a few people who were not agreeing to the fundamental plane, the main question was, oh, you're fitting like stellar mass black holes, which are like apples, and supermassive black holes, which are like oranges together, like it can be a force fitting and stuff. But here, we could show that we are just fitting the supermassive black holes. We are just extrapolating it, and we are putting the X-ray binaries information, the information of the stellar mass black hole here, and without fitting also, they follow the same exact trend. So that was a super, very interesting result for us. And this was the basic of the paper. This is the optical fundamental plane of black hole activity. So right now, we did not have too many observations in radio for the supermassive black holes. As I said, we know a lot of supermassive black holes. For a lot of them, we know like either O3 lines or the X-rays or the mass, but the radio sample was very limited. So after this project, I did two other projects, and then in the final year of PhD, I got back to this. And we did a radio survey of the local galaxies to see if we can populate like more supermassive black holes here and refine the parameters of the plane. So we detected a lot of galaxies in radio which were not previously known. So for example, this is just to show you some how they look like. So this is, for example, one of the galaxies, and in the center we think that there is a jet. So basically this is the core of the jet we are looking at. So we did populate the plane quite a lot and refine the plane at the end of the PhD. So here now we have many more supermassive black holes, and the correlation that we get is much tighter now. That was that was the base of the fourth paper that I was working on. So now that we have just like 10 minutes, I will give you a 2-minute summary of the work, and then we can have a discussion on this maybe. Okay, so in conclusion, now you know that we have supermassive black holes, which are mainly at the center of a galaxy, or which are like millions of times more massive than our sun. We have stellar mass black holes, which are a lot. Even in our own Milky Way, we have lots of stellar mass black holes. But we can see them only if we have some gas cloud or some star coming in the vicinity. And there are many differences, but also similarities between these two. For example, we looked at just the supermassive black holes, and we saw that there is a disk jet coupling, or there is a very tight correlation between the jet power and the accretion disk rate, which is also followed by the stellar mass black holes independently. We did some new radio observations, and we found many more stellar mass, the supermassive black holes, which follow the same trend. Okay, thanks a lot. So this is the main presentation that I had that I wanted to talk about. And if you have any question or anything, you can let me know. Now I can see the faces again.
Thank you a lot. Thanks a lot. Yeah, I think it was really interesting, and also we could follow most of the things. I think, although of course it would be the actual work would be almost very difficult to understand. So you have to, for the students, you have to keep in mind that what he showed is mainly the result of the work. But of course, the actual work that has gone into it would be more difficult to understand. But if you find the actual work and the hypothesis that she's trying to prove, actually that is the exciting part. So it's more interesting to understand that, so that you yourself, some of you, can become interested in doing something related to that.
Yes, I wanted to say that thank you for presenting such a comprehensible presentation. Like for non-physics minds like mine, this would be difficult, but through the cool parts and the ones that would actually blow our minds away, and you're presenting in a really comprehensible way, so thank you very much.
Great, thanks a lot.
Yeah, thank you, Miss. It was actually fantastic to see the correlation line of the stellar mass black hole. My mic was muted, but I had to say nice myself, because that was really very cool to see. Because that was an independent observation. That was an independent extrapolation.
Yeah,
right?
that is
as far as I could. So, one question I had was, how exactly do you do these line fittings? What tools or software or programming languages do you use? I'm a CS major.
Oh, okay. So I'll again maybe just show either the paper, or I might have a slide on what we're doing. Yeah. So can you see the?
Yeah.
Okay. So while doing the fitting, we use something called as a merit function. So it's it's like a standard chi-square, but a bit more involved. So yeah, I don't know if we should go too much deep into this, but this is something known as a merit function. I'll send you the paper probably. I'm not sure if it will be easy to explain so that everyone can understand. Like, I'm not so good at statistics to make it easy to understand. But yeah.
All right. Thank you. Yeah, I'm only familiar with the standard chi, not the merit function. I don't really know.
Okay.
Ma'am,
there was another question.
What are the basics to, ma'am? What are the basics to calculate the mass of a black hole?
Of a black hole? Yeah, that's a really great question, because of a black hole, right?
Yes, ma'am.
Yes, I think she asked. Yeah.
Yes. Yeah, that is actually a great question, because we don't know the mass of a lot of black holes properly. But the main thing we are doing, okay, where is that slide? Sorry. Yeah, forget it. So the main thing that we are doing is to look at the stars which are which are rotating, the velocity of the stars which are rotating the black hole. So these are all a kind of indirect measurements. So at least in my study, because we should keep the sample uniform, so we use these stellar velocity dispersions. By looking at how fast or how these stars are moving, we made an indirect measurement of how massive the black hole should be, so that they can make the stars move so fast. Like, the more powerful a black hole is, the more, for example, in a very simpler way, the more powerful the black hole is, the more fast it will be rotating the stars. Also depending on how far the star is from the black hole. But yeah, so the basic idea is that by looking at the stellar velocities, the dispersion of that, we try to get an idea of how massive the black hole is.
Thank you, ma'am. Another question.
Yeah, Khan, you can add, then we can ask the next question.
No, I can add that, of course, most of you are familiar with Newton's theory of gravitation, also Kepler's laws. So those same laws are being used to calculate the mass here. So it would be familiar to you as well. Yes, I think Aisha, you had another question?
Yes, ma'am, does a black hole always travel?
Well, yes. By travel, I mean, so it's not like the black hole traveling, but everything is in motion in a way. Like even in, for example, let's talk about the stellar mass black holes first. So these stellar mass black holes, especially the ones which are inside the galaxy, the whole galaxy is moving anyway. Like there is a supermassive black hole, there are like different stellar mass black holes, and everything, like even our sun or the solar system, they are also moving. Similarly, all the galaxies are also moving, like because every galaxy is going further and further away from each other. So while the galaxy moves, it's like the black hole is also moving. So yes, all the black holes are moving. Yes, I'm not sure if that answers your question, but if you want to go in detail, you can ask.
Okay, ma'am. Thank you. And the space inside a black hole is fixed, right?
Sorry?
The space inside a black hole is fixed. Is it fixed?
I am not sure what you mean by fixed.
I think she wanted, well, if you mean that it cannot grow, that's not actually true, because black holes can grow, of course.
Yes.
Yeah, the surface area of black hole increases.
Yes, if it is accreting more, its mass will. I think that's what she meant, right?
Okay. Yeah, no, it can grow. Yes.
Ma'am, I have a question.
Yes.
So after this work you have done, what's next? Can we do anything after this that's related to this?
Yes, actually. So related to this, there are a lot of things which I have been also wanting to do because, okay, so let's just talk about the optical fundamental plane, for example. So if this is true, if the stellar mass black holes and the supermassive black holes are actually following this trend, then we can build upon that a lot. For example, my second project during PhD was on that, to use the fundamental plane to see more things for it. So when I say that we are using in the fundamental plane the radioluminosity, the X-ray luminosity and things like that, that is the radioluminosity which is very close to the black hole. So we are trying to, because we want to understand the black hole itself, so we are trying to find the radioluminosity of the jet at the very close part of the black hole. But now, when we look at all these quasars, for example, all the different radio galaxies, then a lot of radioluminosities we get are from the far away part, or sometimes all these radioluminosities are highly beamed when they're coming at us because we are directly looking at it. Right. So if we can believe this supermassive black hole and the supermassive black hole correlation, then we can use that to get an idea of the intrinsic power. We can use our observation to see, for example, what is the relativistically beamed power. And then by using these two, we can understand the relativistic effect of these black holes, like of the jets. So that is one of the things that we were doing. And then there are many more. For example, if you can, we can refine the parameters much more. Right now, for example, the correlation that we have has like 0.6 plus minus 0.1 or 0.2. So there is an error bar. If we can fix it more, then we can see even intrinsic effects inside that plane. Like there are some black holes which are spinning. There are some black holes which are not. Right now, these kind of effects we cannot study because the plane parameters are not refined enough to see these kind of, smaller deviations we can't see. These are like, there are scattered in this plane. And we can't completely understand why these scatters are. I mean, why is not everything, if the physics is so simple and beautiful and blah, blah, then everything should follow the exact correlation. But there is scatter. And the observations that we have right now are not great enough to make that scatter smaller or to explain why the scatters are for different black holes. So if we can understand, for example, the spin of black holes through this, that would be wonderful. So there are a lot of things we can build upon that.
So another question was that Are these black holes considered to be Schwarzschild or like Kerr black holes or stuff like that?
Nice. Okay. Yes. So at least in the theory, so there was my supervisor. He was working on the theory part of this, and there we are just assuming all this to be Schwarzschild. Like we are not taking into account spin of the black hole and the Kerr matrix at all right now.
I see. Okay. So one could actually work with Kerr matrix.
Yes. Yes. So so my part was just doing the observational and the analytical part. When we go into the theory, yes, one can.
Okay. Thank you, ma'am.
Ma'am, I have a question. Hello?
Yeah, hi.
Yeah. Why we are observing these supermassive black holes of other galaxies rather than our own Milky Way galaxies?
Nice. Okay. That is actually a nice question, because I'm saying nice because I had the same thing in mind when we started talking about this, like during our masters. So we are in the disk of the galaxy. So we are at, for example, the outer part. So when we want to look at the galaxy, the black hole just in the center, it's difficult for us to see because we are not like seeing from above. It's nice to see, you know, like even in your life, for example, you have problems. It's nice to see as a third person, oh, this is the problem. Like, but when you are in the problem, it's difficult, right? Similarly, okay, you're putting it in YouTube. I forgot. Sorry. So similarly, if you are in the galaxy itself, so it's difficult to see the, to study the black hole in the center of it. Plus, there are actually, it will be wrong for me to say that we are not doing that, because there are a lot of studies right now also which are trying to understand the black hole in our galaxy itself. But the kind of work that I was doing for the fundamental plane, we don't need just one black hole. We need a lot of information. Like, you know, it needs to be a statistically viable sample. And hopefully one day we will be able to put our Milky Way also in the correlation. But right now, you see, we need the radio luminosity also to be, for the galaxy to be, or for the black hole to be in the plane. But the black hole that we have right now, the black hole in the Milky Way, is in quiescence. Like it's not actively eating up everything that is coming. So we don't have any jets or anything from Milky Way. So our black hole is difficult for me to put in this kind of study. But there are a lot of studies which are going on understanding the black hole in our galaxy. Oh, and also to add to this, all the stellar mass black holes that we use, they are from our galaxy.
Oh,
Ma'am,
okay.
I have another question.
Mm-hmm.
Does the star still lights up inside the black hole?
Sorry, I did not understand.
Does the star still lights up inside the black hole?
Does it light up inside the black hole?
Yes, star after it heats up.
Okay, inside the, so again, I can talk about ideas and stuff, but my specialty is outside the black hole, like, you know, very close to the black hole, but not inside enough. So I think maybe even Khan might know better than that. It's more of a theoretical person who can answer it better, probably. Khan, help.
So as far as I know, once something is inside a black hole, it is lost. So you cannot ask anything like that, actually. So that would be a wrong question. It would be something like asking what was before Big Bang, probably, because once something is inside a black hole, you just care about its mass and probably some other parameters as well, but nothing more than that. So everything loses its individuality. So that's a good thing in a way.
That means inside a black hole there can be also a universe, right?
Well, those are more theoretical things that people sometimes do, but I don't think we can discuss about this enough here.
I think we're delving into the realm of philosophy here.
Yes.
For example, there are many, if you're doing theoretical, well, of course, if you're doing theoretical physics, people do work on many things, like can you get a Big Bang out of a black hole? But we don't know the answers to those questions. But of course, they are interesting to think about.
Okay, thank you, sir. Pardon me if that was a silly question.
No, it was not silly. Like
It's a question
it's
that
nice
we're
to
working on now, right? So
Okay. Thank
yeah.
you, sir. Thank you, ma'am.
Yeah. We used to discuss these kind of things when we were in masters. Khan used to say a lot of philosophical stuff regarding these kind of things. So yeah, you are in good hands. You should make Khan speak sometime without recording probably.
also maybe it would be interesting to add, like, where did you get the optical data from?
So yeah, actually that's a good thing, because if you also want to do, it's very easy to do right now. So optically, SDSS, there is a database which is available publicly for everyone to use. So the optical data, I did not do anything. I just went to the archive of the website of SDSS database and used everything that they had. Radio, some of the observations I did myself, as I did show, and some of them were from previous papers. So that is actually really nice about astrophysics, and maybe also some other physics or sciences, but that once you have the paper published, you kind of put it out for public, and you can use all these radio mass and stuff. So for radio, for example, the new observations that I did, I was using the VLA telescope, which is in New Mexico, I think. Yeah, New Mexico in the US. And that is an array of telescopes. So it's not just one telescope looking at the sky, but it's a radio interferometry. So it's, yeah, you guys might know the ones at least who are working on the engineering part probably. So it's radio interferometry, a lot of disks which are looking at the same place at one point of time and trying to get information. So for radio, I used my own observation. Baki sab, everything else is from
X-ray from where did you get the X-ray data?
X-ray was also from, I think mainly, well, a lot of different telescopes probably, but mainly we used the Swift X-ray telescope data. But those are also like archives. I did not do any observation.
So there would be like standard catalogs that already has X-ray luminosity.
Yes.
For
yes. Yeah.
So I think your talk would be also relevant for some people. Well, I don't think they are here because we are in one of our projects. People are working on classifying radio galaxies. So exactly based on their jets.
Yeah, I think some people have been interested to be here.
But I think they are not here. People who are working with that. So, but in any case, so it is relevant because we're like one group is working on how you can classify radio galaxies. Radio galaxies, again, I'm using radio galaxy instead of AGN, same thing for now. So how you classify these galaxies into different categories, for example, FR1, FR2. So actually we are doing a project where we want, well, this has been done. We're not doing anything new. This is more for the students to learn that you can classify FR1. So there are mainly 3 types of galaxies, FR1, FR2, and there is another thing called bent galaxies. And using machine learning, we can try to classify them more efficiently. So actually, computer science people became interested in that, and they're trying to do that. Using,
nice.
So that is exactly relevant to this topic because that jet is exactly coming because of that, the same mechanism that you were talking about. And also, in another of the project we probably will be working with galaxy clusters. And many of the galaxies are usually within a galaxy cluster. And their jets actually affect the environment of the cluster also. So I think there are a lot of work also on how the jets affect the cluster environment and things like that. So yeah, I think there are a lot of things that will be relevant for us as well. And probably in the future also, Payaswini will come back to talk more about what she has done next.
Or to hear when you guys are talking.
Yeah, that although if you're talking in Bangla, then probably you wouldn't understand that much.
But Bangla বুঝতে পারি.
Yeah, so your Bangla is not that bad, but still you wouldn't understand more.
Yeah.
So, but if it is in English, of course, or in well, you're welcome to join anytime. So we'll keep you invited in the journal club.
Okay, nice, great.
Maybe we can talk again. Any other questions from anyone?
I have a question, ma'am.
Yes.
Yeah.
Can a larger black hole can eat up a smaller black hole?
Yeah, eat up, like more like a merger. Yes. So whenever a merger happens, it's like eating up only. Like, but yeah,
Oh, okay.
they can. Yes.
Okay.
Also, I think you can look back in YouTube. There are interesting simulations of how galaxies merge together, and if there is a black hole inside them, those two black holes will also merge together. So there are interesting simulations in YouTube.
So, which types of softwares are used for analyzing data?
So, well, radio, we are using mainly APES or CASA, which are both completely dedicated radio software, radio data analysis softwares. Actually, CASA is easy to use. APES is a bit more difficult. I think, Khan, you're working with LOFA data now or not?
Yes, and so local community doesn't use Kafka that
APES.
much, but because, but yeah, I think they're using Kafka. But of course, these are more specific than. But it would be, if you're interested to work on this, then yes, we can talk more about what kind of software. For different, maybe I would add that for different types of instruments. So there are no standard software in astronomy. It's more about like community, which community you are working inside. So your software will be made by that community, also specific to that community.
Yeah, I can only speak about radio. Yeah, sorry.
As data is available on SDSS or any other archives, can we do any small projects with this data?
Yes,
at just a personal level for my interest? Is it possible, or how to do it?
So I think Khan will be able to guide you on where to find the data. Like there are a lot of databases for X-ray, radio, and radio not much, but X-ray, optical, at least there are a lot of archives and stuff. And the only thing is that if you publish anything, then you need to give the credit or citation to that. Okay, this is where I got the data from and stuff like that. But otherwise, these are free to use.
Yes, and also, of course, like if I don't know if you will be interested, but if someone wants to work specifically something related to what Payaswini is working on, she might be able to help you as well. So you can contact me, and of course I know her. So if you want to do something very specific to what she is doing, then of course, yeah, we can. Maybe she will be able to help. And for the data, for example, in some of the projects we are trying, the first thing that we would want to teach to students is how to get publicly available data first, so that you can do your own thing first, just to learn, not publish anything. Of course, to get there, you need to work more. But yeah, that's very interesting. So if you're interested, of course, you can contact us, both me and Payaswini also. Throughout.
Yep.
Okay. Anything? I think we also ran out of time. It's already 10 minutes over time. But in any case, now I think we have to stop. Thanks, Payaswini, again. It was a really nice conversation. I hope that we will come back again to discuss more, because now we know at least some of the things that you have done, so that in the future it will be easier for us to understand.
Yeah, and thanks for having me also, and thanks for being a nice audience without making me feel like that, you're going to like grill me with questions or something. So thank you for being so nice.
Thank you.
Great. Okay.